Is the Assistant Department Head of Advanced Technologies. He's here to talk about the Hyperion Project, the world's largest Linux cluster test bed for high-performance computing research. Please, let's give a warm round of applause to Mark Seagar. Come on.
In particular, all of the vendors that you see up here, the Lustre folks, the Linux ecosystem, the Intel ecosystem, and InfiniBand ecosystem, they all had places to do development, but none of the partners had a place to do the development, testing, and most importantly, scaling of the research. So this collaboration last year won the Federal 100 Award as one of the best federal projects of the year. These are the initial founders. What I'm here to talk about today is the extension of Hyperion to include Appro and Fusion IO. And basically, these members contributed these things, and we're working on scalability of Linux with Red Hat and others, and doing Lustre with Oracle, and now the OpenSFS community. And we're working with the OFED community on the InfiniBand software stack. So what we're seeing today is that the I/O requirements of high-performance computers are far outstripping our ability to provide the I/O necessary to meet those requirements. So what we're really trying to do here is to find a new paradigm where we can have a scale-out infrastructure of I/O devices on a SAN, and we're evaluating both InfiniBand technology and 10 gigabit Ethernet technologies, and also what topologies should be, those SANs should be deployed as. Most SANs today are built as ad hoc networks, which means they don't have any systematic topology to it, or it's built as a fat tree. And both of those have some problems with scalability. In particular, you have to take a fat tree down to add to it, which is, and rewire the whole thing. That's sort of bad. So we're looking at innovative technologies like this Tor mesh idea, which allows us to add new vertical segments by breaking one half of the torus and never taking the SAN network down. And that's really important in a production environment. The other thing we're doing is looking at innovative I/O technologies with partners to shape data-intensive computing, and that's the thing that we'll be talking about today. The two things that we're actively looking at is the virtualization of storage devices with one of the Hyperion partners, Data Direct Networks. The benefits of that are tremendous. We think through virtualizing the RAID controller hardware, we can run user applications and the file system right on top of the RAID controller and significantly reduce the latency between the I/O requests and the delivery of those I/Os when they're coupled with flash memory, which I'll talk about on the next slide. So this is a completely new paradigm. It allows us to do distributed data analysis on the RAID controllers, and we're at the moment trying to evaluate how to field these systems and how to do resource management of user applications on that. So this is the Fusion IO SAN card. It has a whole bunch of NAND flash on it, 1.6 gigabytes of bandwidth, 200,000 IOPS, and about 30 microseconds latency, which is superb when you put that into a commodity server, right? And that's where your RAID controller is. You can really drive very high IOPS rates directly to the application that way. And then what we're doing with that is thinking now that we can run our simulations cluster described here by the Hyperion machine, and then do databases or data analysis down on the RAID controller, and then the only communication between the data analysis and the cluster are the results. Instead of transferring all of the data back and doing the data analysis up in the cluster, saves us a tremendous amount of bandwidth. And the bandwidth, one of the key requirements, bottlenecks that we're not able to meet right now, is the bandwidth between the large machines and the I/O resources. So one of the things that we were faced with in building Hyperion was we needed to take a terascale, this is a 100 teraflop resource, and mimic the I/O requirements and resources that will be required for Sequoia, which is going to be a 20 petaflop machine. So that's 200 times more powerful than this machine, and do it in such a way that we can test out technologies that will be ready in the Sequoia timeframe. So what we did was we actually extended the backbone of the Hyperion machine, the backbone network, so that we could have additional ports to that. This is very unusual for a compute-intensive cluster. And now we have 1.3 terabytes of I/O bandwidth in and out of the cluster from all the nodes in aggregate in each direction, total of 2.6 terabytes per second. That allows us to have a huge amount of bandwidth on this thing. So the next component that we found for this I/O testbed was commodity servers that take up a very small form factor. This is a motherboard from Supermicro. It fits into a 1U node. It's got dual Westmere 12 cores total there. It's also got 24 gigabytes of DDR3. It's got 4 PCIe Gen 2 by 8 slots, which is amazing in a 1U form factor. So that's where we put the two of the Fusion IO SAN cards. And in addition to that, we put their standard card in there that doesn't have the interconnects on it for a total of 4 cards. And we enabled one port off of each of the IO SAN cards to do a 40 gigabit quad data rate InfiniBand. And we also enabled 10 gigabit Ethernet so we could plug it into both of those SANs and evaluate various protocols and technologies for expanding our network. And we also had 2 1 gigabit Ethernets, and even though, comparatively speaking, that's like 50 times slower than the other stuff, the reason we have that there is so that we can compare what cloud computing guys are doing today with 1 gigabit Ethernet against what you would want to do with this technology in a high-performance computing environment. So in addition to that, and to complete out the cloud storage comparison model today, most cloud storage boxes have 2 SATA drives or 2 SAS drives, so that's what we put in there. So now we can compare all this stuff against the standard cloud configuration. So one of the things that we did this year for Hyperion was to upgrade the network to quad data rate. This is the network diagram for that. We kept a very large number of switches up there, and as I mentioned before, we have a large number of ports coming off the spine backbone that now allow us to hook it up to our entire environment. And what we deployed with our colleagues at Appro and Supermicro and Fusion IO was 80 of these 1U Westmere things, and the bandwidth of this resource is phenomenal. We got 110 using the Fusion IO cards as a local file system. We delivered 110 million IOPS at 4K, which, I don't know of any other resource on the planet that it can even come close to that. And the other amazing thing is that we got really good IO bandwidth out of it. We got 505 gigabytes per second for 4 megabyte blocks. And the 1 meg block size here is exactly the size that Lustre uses. So that's kind of the number, the base I/O rate that we're seeing with Lustre. In comparison, a DDN 10 drawers through a server gets you about 15 gigabytes per second. So, we're talking about a factor of 20 to 25 there. And this is SRP results. We don't just care about how fast we can deliver I/O on the box. We want to be able to transmit it across the network. So this includes the InfiniBand overhead. It's basically taking a Fusion IO block device that's on one node and exporting it to one of the other nodes via the SCSI remote protocol of InfiniBand. So this uses one of the lowest layers of InfiniBand protocol. And the results here are outstanding. Over there on the right-hand side, you can see from 80 nodes in aggregate, we got about 416 gigabytes per second, which is fairly close to the 505 gigabytes per second that we got from the local device. So that exporting it there is actually fairly low overhead, assuming there isn't a file system in the way. So the next thing that we want to do with this resource is to layer Lustre on top of it. We're actively engaged with a company called WAM Cloud to look at these nodes as both metadata servers for Lustre and object storage targets for Lustre that use the flash I/O, and to see where the bottlenecks are when we do that. So this has computing power in the top 20 now of the top 500 list. Hyperion is the world's fastest data-intensive computing environment. It's amazing the number of industrial partners that are interested in this thing, and by leveraging this existing test bed, it was a minimal incremental investment to add this data-intensive test bed. And just to let you know, in the last year, we've put the California utilities and the California Public Utilities Commission on this machine, and we're doing grid modeling now, utilizing this resource in support of energy activities. So with that, I'll stop, and thank you very much.